Hello! Today we will discuss the foundations of probability theory and how to derive basic theorems from it. We can start with the most fundamental question. What is probability? This is very hard to answer since probability has many different possible interpretations, so we will actually be avoiding answering this. Instead of asking what it is, we will ask how it behaves. How do probabilities behave? To properly formulate this in the probability axioms, we need to introduce some concepts first. Firstly, the sample space. A sample space is the set of all outcomes for some experiment, usually denoted omega. So an element in a sample space is called an outcome. A simple example of a sample space is flipping a coin. We either get heads or tails. If we flip 2 coins, we get 4 possible outcomes. Now, it is important that we think about what our experiment is. When we flip a coin, the coin ends up somewhere on our table or in our hand, but we all recognize that the only thing that matters to us is which side that faces up. In reality, we could expand our sample space to account for these variations, but they are not relevant to us, so we ignore them for a simpler model. We could just as well reduce our model here if we wanted a different experiment. Say that we only care about how many coins turn up heads. Now we only have 3 elements in our sample space, which denote the number of coins that ended up heads. We can even have infinite sample spaces. How tall someone under 2 meters can be is an infinite sample space. It is infinite because someone's height can be any real number in the interval 0 to 2, not including 2. They can be 1.5 meters, 3/4 of a meter, or pi over 2 meters tall, for example. Now, we introduce the event space, here denoted by F. An element in the event space is called an event. This is the power set of the sample space. If you don't know what the power set is, don't worry. The power set of omega is the set of all possible subsets of omega. I think an example helps here, so let's get back to the 2 coin flips. This is what the event space would look like. Note that we could describe these events with words. This event describes getting heads. This event describes every outcome. It is the sample space itself. So an event refers to a subset of possible outcomes. The event space is usually what is interesting, not the sample space, but it is important to recognize where the event space comes from. All that is relevant about the sample space most of the time is that it is big enough that we can distinguish between different relevant events in our experiment. We can perform standard set operations on events. The intersection between the event that I drank water this morning and that I ate a sandwich is intuitively the event that I did both. In this same way, you can take complements of events. The complement event to me eating a sandwich was that I did not eat a sandwich. The union of 2 events would represent the event that either of the events occurred. Now, we go back to the question, how do probabilities behave? We introduce a probability measure, denoted p. This is a function that maps from the event space to the real numbers. We construct this in the aims of having a function that takes an event and spits out its probability of occurring, whatever probability means. Now, we introduce the probability axioms that describe how this function must behave to rightfully be called a probability measure. These axioms are called the Kolmogorov axioms. Axiom 1. The probability of any event is a non-negative number. This makes intuitive sense and seems almost too obvious to state to most, but there are alternate probability theories that incorporate negative probabilities in a meaningful sense. Those theories' probability measure would not be a probability measure according to these axioms though, so they modify the axioms. Axiom 2. The probability of the entire sample space is 1. This could be read as, something has to happen. Even if we had a result in our experiment that was nothing happened, then that would still be an element in the sample space, a possible outcome. Axiom 3. This is the hard one. Any countable sequence of pairwise disjoint events, A1, A2, and so on, satisfy that the probability of the union of all the events equals the sum of the probabilities of the events. What do all these words mean? Countable sequence refers to countable in the set theory sense. You could theoretically list them in some order given infinite time. Pairwise disjoint means that given any pair of the events, there will be no intersection between them. So how do we get intuition for this third axiom? We could start by thinking only of a finite number of events that are not the empty set. This is equivalent to then adding a finite number of events. An example would help here. Say that I have a favorite color, unknown to you. Let R be the event that red is my favorite, B that it's blue, and Y that it's yellow. It's also possible that it's some other color. We know I have one favorite color, so R, B, and Y are pairwise disjoint. We can therefore, according to the third axiom, say that the probability of my favorite being either red, blue, or yellow is the same as the probability that it's red plus the probability that it's blue plus the probability that it's yellow. This should make intuitive sense. The third axiom allows us to do this with a countably infinite number of disjoint events. Using these foundational axioms, we can prove some simple theorems. We can prove that an event being a subset of another implies that it has a lower probability of occurring. Let A and B be events such that A is a subset of B. We want to prove that the probability measure of A is less or equal to the probability measure of B based on this assumption. B can be written as B without A union A. This means that P of B is P of B without A union A. B without A and A are obviously disjoint, so we can say that this is equal to P of B without A plus P of A. Now we use the first axiom. Since P of A plus some non-negative number becomes P of B, and P of A and P of B are also non-negative numbers, P of A cannot be greater than P of B, which is what we were intending to prove. Please feel free to pause and convince yourself of every step of the proofs I show. Next up is another easy theorem. The probability of the empty set is 0. Observe P of A for some event A. We can rewrite this as P of A union with the empty set. Since the empty set is disjoint with every set, we can use the third axiom and say that this is equal to P of A plus P of the empty set. Now subtract P of A on both sides, and we get what we were intending to prove. Another simple statement to prove is the complement rule. The probability of the complement of an event is 1 minus the probability of the event. Remember this one. I will use it many times this video. Start from the second axiom. Rewrite the sample space as the union of an event A and its complement. Since an event and its complement are disjoint, we can use the third axiom on them. Now simply subtract P of A on both sides and boom. The last easy statement to prove before I introduce more theory is that the probability of any event is between 0 and 1. The lower bound is given directly from the first axiom. We can use monotonicity. Set the larger set to the sample space itself and use axiom 2 to get the upper bound. A is always a subset of omega by definition. Now, 2 more theory. Conditional probability. Let A and B be events and assume P of B is not 0. We define P of A given B as P of A intersection B divided by P of B. How do we interpret this? Think of it as the probability that A occurs given that B has occurred. It might be easier to understand if we write it as the probability that A and B occurs is equal to the probability that B occurs times the probability that A occurs given that B has occurred. I think an example is necessary here. The probability of your favorite sports team losing the first game of a season is 0.5, 50%. The probability of your favorite sports team winning the 2 first games of a season is 40%. What is the probability of winning the first 2 games given that our team already won the first game? Let A1 be the event that our team won the first game. Let A2 be the event that our team won the second game. We can quickly figure out what the probability of our team winning the first game is. Use the complement rule. Note that we assume that there cannot be any form of draw in this sport, otherwise losing is not the complement to winning. Then we get that P of A1 is also 0.5. Note that the probability of us winning both the games is P of A1 intersection P of A2. What are we looking for? P of A1 intersection A2 given A1. The screen is getting a little cluttered, so let's remove the old information for the question, since we've formulated it in explicit events. Use the definition of conditional probability. We get P of A1 intersection A2 intersection A1 divided by P of A1. Rewrite this as P of A1 intersection A2 divided by P of A1. These are both known, so we get 0.4 over 0.5, which yields 4/5 or 0.8. The probability measure given some event is also itself a probability measure. We can conclude this by seeing that P given B fulfills all the probability axioms. Let's start with the first axiom. P of A given B can be rewritten as P of A intersection B divided by P of B. Since both the numerator and denominator are non-negative, the entire fraction is non-negative, which yields the first axiom. Now, onto the second axiom. P of omega given B can be rewritten as P of omega intersection B over P of B. Then we get P of B over P of B, which is 1, since B is a subset of omega. Second axiom fulfilled. Now, there's only the third axiom left. Observe P of a union of disjoint events A1, A2, and so on, given B. Use the definition of conditional probability. Use the distributive law between the union and intersection. Since all the A's are disjoint, the A's intersected with B will also be disjoint. Use the third axiom for our already established probability measure. Now do a few short manipulations, and then the definition of conditional probability to get what we are looking for. It should make intuitive sense that conditional probability measures are probability measures, because in a way, all probabilities are conditional probabilities. Whatever statement you can dream up to assign a probability to, it has some underlying assumption, some event that has already occurred. If you want to calculate the probability of your sports team winning a game, you are assuming there will be a next game your team plays. What if all the players on the team quit tomorrow? You're probably calculating the probability of them winning, given that they play, and the game is finished, and whatever assumptions you have about the world. Now we walk away from the philosophy and continue. If we partition the sample space with some events A1, A2, and so on, then the sum of the probabilities of the A's is 1. You might ask what a partition is. If some sets partition the sample space, then every element in the sample space belongs to exactly one of the partition sets. The image you should have in your head is this illustration. The red circle is the sample space, and it is cut up into bits that partition it. This theorem can easily be proven from the second and third axioms, since the partition sets are disjoint and the union of the partition sets form the sample space. We can partition any other event B with a sequence of C's, and conclude that the sum of the probabilities of the C's equal the probability of B by the same logic. It is time for another example. What is the probability of me winning a chess game? Let's say we play with a clock, so I can win by checkmate, or that my opponent runs out of time. Let's say that W is the event of me winning the game. We are looking for P of W. Let A be the probability of me winning by checkmate, and B the probability of me winning by timeout. A and B partition W. This means that we can rewrite this as P of A plus P of B. I will not put numbers to this example to protect my ego. Now we can continue to the first of two big useful theorems we will show. First up, the law of total probability. Let B be an event, and A1 and A2 and so on be events partitioning omega. P of B can be rewritten as the sum of probabilities of the A's intersected with B. We can say this because the A's individually intersected with B partition B itself. Now use the second formulation of conditional probability on every probability measure on the right-hand side. This will yield our big theorem. How can you use this? Example time. What is the probability that our soccer team wins? We know that the probability of our team making the first goal is 0.6. We also know that the probability of our team winning, given that they have made the first goal, is 0.8. The probability of our team winning, given that they haven't made the first goal, is 0.4. How do we solve this? We start by using the complement rule to figure out that the probability of our team not making the first goal is 0.4. Since making the first goal and not making the first goal partitions the sample space, we can use the law of total probability. P of win equals P of win given the first goal times P of first goal plus P of win given not first goal times P of not first goal. Put in numbers and calculate. 0.8 times 0.6 plus 0.4 times 0.4, which becomes 0.68. Our team is favored to win. Note that we assume that a first goal will occur. Now, the last big theorem we'll go over, and probably the thing you'll be left thinking about at the end of the video. It's called Bayes' theorem. It looks like this. The theorem is actually quite simple to prove given our already established theorems. P of A intersected with B equals P of B intersected with A, because the set intersection is commutative. Let's use the second formulation of conditional probability on both sides. P of A given B times P of B equals P of B given A times P of A. P of B is by assumption not zero, so we can divide by it on both sides. This yields Bayes' theorem. This is a profound theorem that relates A given B to B given A. Now, for an example. Let's say there's a disease we want to be tested for, very relevant in these times. What is the probability that we are sick, given that we get a positive test result? Let A be the event that we are sick, and B the event that we get a positive test result. Use Bayes' theorem. We know that P of B given A, which is the probability of getting a positive result given that we are sick, is 0.99, 99%, for our test. Let P of A, the probability that we are sick, given no information, is 0.1 for our disease. The last and hardest piece to solve is P of B. What is the probability of getting a positive test? There are two possibilities. We get a true positive, we are sick and we get a positive result, or we get a false positive, we are not sick, but still get a positive test result. Notice that sick and not sick partition the sample space. We can use the law of total probability. P of B equals P of B given A times P of A plus P of B given not A times P of not A. We can use the complement rule to figure out that the probability of not being sick is 0.9. From our test, we can get the false positive rate. Let's say it's 0.02, 2%. Plug all this information in and calculate. Now move this a bit so we can do the last step. This becomes approximately 0.846. This concludes my introductory material for probability theory. I feel like probability theory is often neglected in online educational content and usually introduced poorly in education, so I hope I could spark some people's interest by introducing it in a novel way. What I showed here does not even scratch the surface of probability theory, so please explore more for yourselves. Bye!